Shamik Gupta from TIFR Mumbai with us today. So Shamik is a statistical physicist by training. He did his PhD from TIFR Mumbai with Mustansir Verma, following which he had 3 postdoctoral stints. One is in Weizmann Institute, Israel, the École Normale Supérieure in Lyon, France, and then LPTMS University Paris Sud in France. He then held a visiting scientist position at the University of Florence and later became a guest scientist at the Max Planck Institute of Complex Systems in Dresden. Shamik returned to India in 2016 and took a faculty position in the Ramakrishna Mission, Belur, and where he stayed till 2022. And only very recently, 2 months back, he has joined TIFR Mumbai as an associate professor. Shamik has various interests, so out of them a few are non-equilibrium statistical physics, long-range systems, nonlinear systems, synchronization, and quantum dynamics. Today he is going to give us an overview of the fascinating story of synchronization. And those who are interested, Shamik also has written a beautiful book on the topic, and I'm sure we will get to hear more about it during the seminar. Okay, Shamik, so the stage is yours. Thanks.
Is this going to happen like again and again?
Switch off the screen saver.
No, that it did. This game, but okay, let's see if it happens. Huh? Happen again. So let me just see if it is working. Okay. Yeah, I think okay. So let me start by thanking Shayantan for the invitation and Varna for the kind introduction. I'm very happy to be here to give the special colloquium on the occasion of this anniversary of your institute. So I'll be talking about some work that I have been involved in for, let me see this one, yeah, for the last, I don't know, 4 or 5 years, mainly with students and postdocs, based on some earlier work that I had started working on during my PhD day, so during my postdoc days. So what is it that we are going to talk about? We are going to talk about spontaneous synchronization. What is it? So I'll show you, hopefully the video is working. Yeah, so the first picture is that of, is the pointer working? Yeah, okay, yeah, now it's fine, thank you. Yeah, so the first picture is, I guess we all know what it is. It is because we are here that, we know what it is, that this is the picture of beating heart, okay? And what you can see is that, there are these ventricles and, they are beating at a particular frequency. You see that, these things, they kind of compress and then blood is flowing out and then there's an expansion and blood is flowing in. But what you see from this picture is that this is happening at a particular frequency, right? It's not random. And had it been random, we all would not have been here. We would have been in some other world, okay? This is the picture of beating heart. What is this picture showing? If you, concentrate, then you will see that suddenly there is this sudden flash of light, right? I mean, if you see that, you see a big flash of light occasionally, maybe because of light contrast, it's not coming very clearly here. You can go to YouTube and search for this. What is it? So this is the picture of fireflies. I guess we all have seen or have heard about fireflies, especially in my childhood, in my city, which is Calcutta. We did have fireflies. I don't know where they are now. So what is happening is that these fireflies, the male fireflies, what they do is that in the evening time, they gather on trees. And each of these fireflies has the ability to flash light at a particular frequency. Each one has got its own frequency of flashing light. But then what happens is that when a large number of them gather on trees, out of nowhere, they start to flash together. Okay, and that's what this picture is supposed to show. As you can see, there's a big bunch kind of flashing together. The frequency at which these flashes, come out is different from the individual flashing frequency of the fireflies. This picture, I'm going to show a video. What is it? So this is about clapping audience. I mean, this is something that we must have, realized and appreciated. namely the following situation, that you go to a concert or to a movie, a good movie, hopefully, and again this one is happening. Yes? Huh? He did something. Yeah, so while they are trying to fix it, so let me explain the situation. The situation is that there is a concert and there is a performance, and then at the end of a performance, if the performance is good and when the performance is good, then the audience start clapping. But when they start clapping, initially, each one of them claps at his or her individual frequency, but then after a short while, you feel as if the whole hall or the theater hall or the concert hall is kind of clapping together. So I'll just show a video of it. So like initially, you please make a note of it, that like initially there should be, let me see if I can do it. So this. Now you see everybody is clapping together as if. And then of course it remains off. So hopefully you got an idea of what I'm talking about. You must have seen it, sorry. And this another example is that of power grids. I mean, this is also a picture that we must have seen. So in power grids, what happens is that you are given a network, network of generators and motors. Okay, generators are there at the electric supply station, and motors are there at the consumer end. And typically, what a generator or a motor comprises is you have a shaft which is rotating in a magnetic field. I mean, in the case of a generator, the shaft rotates and that generates electricity because of Lenz's law. And while at the motor end, what happens is that you supply electricity to rotate the shaft. And what you have is you have a large number of such shafts like generators and motors, and they are in interaction with one another because there is a supply line to which each of these units is connected. But then they operate, individual unit has got its own frequency, but then they operate at a common frequency, the grid frequency or the line frequency, which for India, I guess, is 50 Hertz. So these are examples of systems which have the following characteristics. Namely, that what you have is you have interacting units. You have many, many units. Each one of them is capable of generating pulse at a particular frequency. Okay, there's a particular characteristic waveform. For example, think of the heart. Of course, it has got a characteristic waveform, a particular amplitude, a particular frequency, like different cardiac cells that make up the heart. Each one of them has got a different frequency and a different amplitude, but then they are interacting with one another in such a manner that spontaneously, that is without the influence of any external field, each of these units are kind of synced up in the sense that they are able to generate a common signal which has got a frequency and an amplitude which is independent of the frequencies of the individual units. So that's the phenomenon of spontaneous synchronization. And so what are the main ingredients of synchronization? So the first one is you need individual unit, like you need a large number of cardiac cells. And of course, then they interact with one another, and that generates the beating of heart. So you need each unit to be exhibiting self-sustained oscillations. What do self-sustained oscillations mean? Self-sustained meaning that each one is capable of generating pulse by having, by exhausting or using up its own source of energy. There's a source of energy that is generating some oscillation at the individual level. But then the main thing is that each unit is capable of doing or generating this pulse that has got a characteristic waveform, okay, namely a characteristic frequency and an amplitude. That's one. And secondly, there has to be some interaction, because what I want is, I want this huge collection of many, many cardiac cells or many, many power grids to be interacting with one another in such a manner that eventually the whole unit is sending out a signal at a common frequency. That's the second ingredient. And well, let's just go over these things a bit more carefully from a physicist point of view. So what I said is that you need a characteristic waveform. What do I mean by characteristic waveform? What I mean is that the waveform has got an amplitude and a frequency of oscillation which is independent of the initial condition of the underlying dynamics. You may think of simple harmonic oscillator, let's say damped simple harmonic oscillator or just normal simple harmonic oscillator. That doesn't generate a characteristic waveform. Why? Because the waveform has got an amplitude and a frequency that is dependent on the initial condition. That I don't want. Like whatever be the initial condition, the waveform should have an amplitude and a frequency that is independent of it. Think of your cardiac cells. I'll give one example of what demonstrates that your cardiac cells are indeed capable of generating such waveforms. So you need a characteristic waveform, and therefore in technical terms what you need is in the phase space. I hope you all are familiar with phase space. What is phase space? So whatever is the unit of the system, so it is characterized by some degrees of freedom, and this phase space is a space whose axis is spanned by the different degrees of freedom of the system that you have in mind. For example, for a simple harmonic oscillator, the phase space will be constituted by the position and the velocity. Okay. So in the phase space, of course, since you want a periodic solution, so therefore in the phase space you have a periodic orbit, but then this periodic orbit has to be isolated. Why it has to be isolated? Because only an isolated orbit has got a frequency and an amplitude which is characteristic of that particular orbit, such that, like here I have shown this isolated orbit in red. Since it is characteristic, so what is going to happen is that if you start from any initial condition, let's say this is one initial condition and this is another initial condition, the dynamics is such that eventually you approach this red curve. So there is, for every unit, there is a characteristic red curve such that whatever initial conditions you initiate the dynamics with, eventually you approach this characteristic closed path, what we call a limit cycle, and it is a stable limit cycle. Why it is stable? Because whatever perturbations you add to the system, eventually you get to this particular waveform. So this at once tells you that the underlying dynamics of the system has to be necessarily non-linear. Why is it so? Because one property of linear dynamics is that if you have found one solution and you multiply it by a constant, the multiplied solution, the multiplied form is also a solution, and therefore you cannot have an isolated orbit in the phase space, because like you take one orbit, you multiply it by number, you get another orbit, and so on. So that means your phase space is going to be constituted by a large number of orbits which are lying very close to one another, and therefore if you are on one orbit and if you make a perturbation, you will jump to another orbit. Think of the phase space portrait of a simple harmonic oscillator. You have this like ellipse in the PQ space where Q is the position and P is the momentum, and you confine yourself to one of the phase space phase space manifold or phase space orbit corresponding to a given value of energy, and you do a perturbation, you give a perturbation, you jump to another orbit, and that's quite incommensurate with this picture. This picture is that you have one orbit such that whatever initial condition you start out from, you eventually approach such an orbit. So therefore the dynamics is non-linear. That's the first thing to keep in mind. Secondly, what you want is, you want a waveform that has an amplitude and a frequency of oscillation that is independent of the initial condition. So think of weird initial conditions. Maybe you start out from a condition which is very different from the one that generates this closed orbit. Then in your dynamics there should be a mechanism such that this one is keep happening. Okay, so then in your dynamics you should have a mechanism such that if the amplitude of oscillation, depending on your choice of initial condition, if your amplitude of oscillation tends to be very small, then there is a source of energy pumping in the system, in the dynamics, that kind of pumps it up. Or the contrary situation is, if the amplitude of oscillations tend to become very large, then there should be a dissipation mechanism in the system that would damp it down. right? Because you want let's say you want a waveform that has got, let's say, 1 centimeter amplitude and a frequency of 1 hertz. So the dynamics should be such that if the amplitude becomes 50 centimeter, then eventually because of dissipation, that sort of oscillatory behavior is damped down. Or a contrary situation is if the amplitude tends to become very small, then there should be an energy pumping mechanism so that those oscillations are pumped up. So you need to have these two ingredients. One is the dynamics should be nonlinear. I'm talking about the individual units, your individual cardiac cell. And eventually I'll of course talk about the whole heart, but at the moment I'm talking about the individual cell. And what I've said just now is that your individual unit should have nonlinear dynamics, that's one. Secondly, the dynamics should have dissipation and energy pumping. And when I say there is dissipation, you can at once conclude that your dynamics cannot be Hamiltonian dynamics, because Hamiltonian dynamics conserves energy. But you want a source of dissipation in the system. So therefore, your dynamics has to be nonlinear and non-Hamiltonian. Okay? So a particular example that I'm going to talk about, and I'll focus on as we go along, is this example of power grid. And just to remind you, must have seen this picture in your high school books, that you have a magnet and there is a shaft, right? Now at the generator end, what happens is that you have to generate electricity. So what is done is that you rotate the shaft. There could be a source of energy due to hydraulic power, or let's say windmill. Okay, there's something that rotates the shaft. So this is the shaft, and as it rotates, it cuts the magnetic lines, and that generates electricity. Okay, so this is happening at the generator end, namely at the power station. While at the motor end, namely at our end, and we are consumers, what happens is just the reverse, that electricity is supplied to us by the power station. We use this electricity to this electricity is passed, and then the shaft starts to rotate. So we are getting mechanical work out of electrical energy. At the generator end, the reverse is happening. Mechanical work is being converted to electrical energy. And what you have is you have a grid. Okay, so here I have shown the power grid of India. So what you have is in a grid meaning that you have many power stations and you have many consumers. Okay, so a grid contains thousands of such shafts. Okay, so these will be self-sustained oscillators. Why? Because every unit, let's say when I'm using a fan, or let's say some unit, every unit has got its own frequency of operation. Okay, there's a particular characteristic frequency at which it operates, or it needs to be operated. And so you have large number of such units. Each one has got its own frequency of oscillation. But the amazing thing is that when I put them together and there is interaction in the system, you get a grid frequency of 50 hertz. And the question is, why does it happen? Because individually they ought to have behaved differently, and they do behave differently when they are put in isolation. But the question is, when there is interaction among them, then some magic happens, which we are going to unveil as we go along. And because of which this conglomerate of generators and motors starts to operate at a common frequency. So the first thing that we as physicists, or I as physicist, would need to do is to write down an equation of motion for the shaft. Okay, so this is rotating. So if you have some unit that is rotating, the first thing to do is to write down, is to characterize the motion in terms of the angle that it has traversed in a particular time, and write down the equation of motion. So what I first do is, at the jth node, you have many such nodes. Chennai is one node, Calcutta is one node, Trichy is one node. Okay, you have many such nodes. What I'm trying to do first is that there is a certain grid frequency. For example, as I said, 50 hertz is the grid frequency. So what I'm doing is I'm looking at the deviation about the mean motion of the shafts. Okay? So this omega t will be the angle that the shaft has rotated in time t on the average, and I'm looking at deviation, which I denote by phi j. The deviation is going to be different at different places. Why? Because not at every places will the angles be exactly rotating at rotating by an amount omega t in t time. There will be fluctuations about it, and the fluctuation is what I denote by this deviation phi j. I put this subscript just to emphasize the fact that the deviation will be different at different nodes, and I would like to write down an equation for this deviation. Why I show this slide? Just to emphasize the fact that on the face of it, this structure or this setup might look a bit daunting and intimidating. Physicists talking about power grids, should we not be talking to electrical engineers? Yes, we should be talking to electrical engineers, but even electrical engineers rely on, and I'm being careful, they rely on principles. The basic principles are all derived from basic physical laws. And what is the basic one physical law that we know of? That is that of energy conservation. We know that whoever does whatever, energy has to be conserved. Total energy that is consumed has to be equal to total energy that is received. Okay? So I write down an energy conservation equation for the jth unit. So what is the equation? So the equation is the following, that I have this Pj source, that is the power which is generated or the power which is consumed. That is, if I am a customer, I receive some power, I will consume it. And what are the different ways in which I will consume the power? So the first one is, of course, I receive something, but of course I give back something to the power grid, right? Because my home, where I'm using my unit, that is connected to the power grid. So the first one is the power exchanged with the grid. That's one. And that, of course, power exchange with the grid, meaning I will be exchanging with the different nodes that make up the grid. So I write it as summation over k not equal to j of this guy. So what is this? The power exchange between two nodes will be a function of the difference in the phase between the two units. Let's say I have one unit k and one unit j, then of course the phase here is theta k and the phase here is theta j, and the amount of power exchange between these two units will be sine of the difference in the phase. Why sine? Because we are using alternating current. Okay, it can be shown from basic like principles of electricity, alternating current principles, that the phase, why this is happening again and again, I don't know. But anyways, so between the unit k and j, the amount of power exchange will be sine of theta k minus theta j, excepting that one thing I have to be careful about. I need to be careful about. What is this? It is the following, that it would take some time for power to be transmitted from one unit to another. So there has to be a time lag. It cannot be that instantaneously power is being exchanged between two units. Okay? Because for example, I'm uttering a word and it takes some time. Of course, that time could be very small, but it cannot be zero. It takes some time for my voice and so on to reach you. So in the same manner, this I have to put a time lag here, because the jth unit is going to exchange power with the kth unit, but there has to be a time lag, because these units are connected by lines, like electrical lines, like transmission lines, and of course there is a finite transmission velocity. That's one source, one way in which I use up my power, whatever I receive. The second one is this power in turbine. What is it? Because what is happening is that, of course, this guy is rotating. Okay, so this shaft has got some inertia, so of course it is rotating, so that requires some power. That is this second guy. This is just I by 2 d theta, ddt of theta dot square, what we know from simple classical mechanics. And the third one is, as the shaft is rotating not in vacuum, but it is rotating in the ambient medium, and therefore there will be some friction because of the ambient medium, typically which it is air, due to which there will be some dissipation. So while the shaft is rotating, it has to do work against the dissipative forces which are at play, and that is this power dissipated in overcoming friction. And when I put all of this together, I get an equation of motion that should look similar to most of you. So let me just, go over this equation a bit slowly. So this is the rate of change of angular momentum. That is equal to, on this side I should be the torque quantity. So what are the different sources of torque? The first one is, this is related to the power which is received at the jth unit, that is Pj. What is this one? This is dissipation. Because the shaft is rotating in the ambient medium, there will be some friction, some dissipation. That's the second guy. And the third guy is the part coming due to interaction between the different units. Okay? So from very basic principles, you can write down an equation of motion for this shaft, which is quite general. I did not have to mention anything about the structure of the grid, but this is just energy conservation. Now, what is it that we are interested in? Why should we be looking at power grids? You have to have some motivation. Maybe I am able to write down an equation of motion based on basic physical principles. That is not enough to embark on a problem. So especially you need to occasionally, justify what you are working on to your funders. So therefore, what is it that we are interested in? That's the issue of stabilization. So what is this issue of stabilization? So it is the following, that let's say you have some disturbance. What sort of disturbance are we talking about? That you have grids, you have a grid, power grid, you have all these generators and rotors, and there's a common frequency. Suppose one of the power station shuts down. Maybe there's some natural calamity or something happens. Let's say there's some technical failure at which one of the grids had to be shut down. So there's some disturbance, and that disturbance, let's say, causes some of the generator shafts to move slowly or faster than the average speed. Then if the grid is working at a stable frequency, typically at the moment I would think that the light is on, therefore the power grid of India is working at a stable frequency. Since it is stable, any disturbance would damp down and the synchrony would be restored. That is, you would still continue to work at the grid would still continue to work at 50 Hertz frequency. But there may be a rare event in which a large cluster of generator speeds up. That is, a very big number of generators start to move at a very high velocity, and then there would be some dangerous power flowing in some of the links, and therefore to save the grid, typically there would be a load shedding. Right? The grid had to be shut down, and if a large part of the grid is shut down, then you have power outage. I'll just give you an example of a power outage. For example, this 2012 Indian blackouts, it was reported that you may have heard about it or read about it in newspaper, that there was a power outage in North India that affected over 620 million people, or half of India's population, and was spread about 22 states. 22 states went out of electricity for a fairly long duration of time. An estimated 32 gigawatts of generated capacity was taken offline. And what this inquiry commission found out was that the major reason was that there was high loading on one particular link, this Bina Gwalior Agra link. So that link was taking from the grid too much power, so much so that the grid had to be shut down, because otherwise there would be chances of some accident. So therefore, the main issues that we would like to address is, given this structure that you have these units, generators, rotors, each one is rotating at its own frequency, the whole conglomerate is rotating at a common frequency, and what we want to know is what are the conditions for synchronization, what are the conditions such that this whole collection operates at a common frequency, and how, once I reach such a state, once this synchronized state is achieved, how stable it is against dynamical perturbation that in course of time you have one unit generating or consuming more power or less power than the average. How does the system adjust to restore the synchronized state? And structural failures, that there is, let's say, a thunderstorm or something and one of the links had to be cut off, and how is synchrony restored in such a situation. Okay, so I come back to my equation. So is there a question like is this equation fine, like at least from physical principles, does it look familiar to some of you? This is just the equation of motion describing how the angle of the jth shaft is changing as a function of time. And what I have taken into account is interaction between the different units and dissipation. Okay. So let's look at this equation and let's look at some of its salient features. The first one to note is that Pj. What is Pj? Pj is basically the power that the jth node consumes or generates. And of course, each node is going to consume or generate different amounts of power. The amount of power that IMSC requires is not the same as, let's say, a Tisco, a company, a Tata company requires. Of course, a Tata company would require much more, a much higher amount of power. So it's different for different units. So in the language of statistical mechanics, we say it's a quench disorder. It's a disorder that is changing from one unit to another, and it's quenched in time. Quenched meaning that it is not changing as a function of time. Here, of course, I am making the assumption that the power requirement of the individual units is, let's say, over the time scale of observation, not changing too much. In principle, Pj is a function of time, but here I am making the assumption that it is not changing too much as a function of time. That's one. Secondly, this time delayed interaction. This is what I talked about, that you are going to exchange power with the grid, but of course it takes time for electricity to flow from one unit to another, because after all these units are connected by transmission lines, and there is a maximum velocity with which you can propagate your signal. So that's time delayed interaction. There is dissipation in the system. This is the dissipation term, and there is a drive term. This Pj, it is the drive, because it is the power, this term, it is this term that is essentially changing phi as a function of time. Now I would like to address the questions that I posed in my previous slide. And what are the non-trivialities? So the non-trivialities are the following. So I have a large number of coupled nonlinear differential equations. Let's look at this equation. Indeed, this equation is nonlinear. Why? Because of the sine term. This term is linear, but sine is a highly nonlinear function. So you have a nonlinear differential equation. How many differential equations are there? As many as the number of nodes, and the number of nodes is not 5 or 10, but you have, let's say, a huge number, let's say 10,000, if not more. You have a large number of differential equations which are nonlinear, and they are coupled. Why they are coupled? Because of this term. You see, I am writing an equation for J, and the J equation involves summation over all k, all the other nodes. Okay? So these are coupled differential equations. There is no noise term here. Okay? So therefore, I need to solve these, these coupled nonlinear differential equations, and unlike what a statistical physicist would like to have, there is no entropy to maximize, no free energy to minimize. Typically in statistical mechanics, you have this sort of setup, that you have an isolated system, a system which is described by Hamilton equations of motion, and the system is isolated, and you want to know in the long time limit, in the stationary state, what is the value of the magnetization, let's say. So statistical mechanics, it is quite easy to do, because it's a Hamiltonian system, isolated. So Boltzmann has told you what you need to do. Second law of thermodynamics has told you what you need to do is, you need to find the entropy, plot it as a function of m. M is the magnetization, and then you maximize the entropy with respect to the magnetization, and the value at which the entropy is maximized is the magnetization that you are going to observe. No such thing here. Or the like other scenario that we are all kind of familiar with from statistical mechanics is, the system is not isolated, but it is interacting with a heat bath, exchanging energy with the heat bath, and then you need to minimize the free energy. If you ask in equilibrium what is the magnetization value that I am going to observe, it is the value that minimizes the free energy. But here I don't know how to do such thing, how to play such a game, because there is no, the dynamics is non-Hamiltonian, there is dissipation, and there is no noise. So therefore, I cannot just maximize entropy or minimize free energy, because I do not even know in the first place what is the entropy of the, if at all there is an entropy function that one can write down. So that's one non-triviality. Secondly, you have phase disorder. As I told you that the amount of power generated or consumed is varying from one node to another. And the third thing is this most non-trivial part of the whole game is this time-delayed interaction. If you think for a while, typically in physics you do not come across many situations where the interaction is time-delayed. Interaction is always instantaneous. Okay, when you write down an equation of motion of a system of particles which are interacting with one another, the interaction is always assumed to be instantaneous. This ith chi is going to affect jth chi at the same instant, not like there is a time delay. So this is the problem that we are confronted with, and we would like to address the questions by solving this set of. So the first thing that we would like to do is that we did in fact, is to map it to a dynamical system, which is the so-called time delayed Kuramoto model. But of course, like as a physicist, what you would need to do, like this problem on the face of it looks very daunting, because you have time delayed interaction, you have disorder, there is no noise, you don't know how to write down an entropy function, you don't know how to write down a free energy. You need to do some approximation. At least as a first step, we would invoke some approximations, and then eventually one can gauge, you know, how good a job you did in doing whatever you did, namely by invoking those approximations. So the first approximation that you do is you want to get rid of at least one source of complexity, that is the structure of the network. The structure of the network is, of course, you have to tell me which country are you going to model. And of course, the first thing that I would like to do is to get rid of the structure of the network and to think of a network in which every node is equally connected or being equally affected by all the other nodes, what is known as the mean field coupling or all-to-all coupling. So you have n nodes. So kj, that is the coupling between the strength of coupling between the kth and the jth node. It doesn't depend on the separation. So it's just all equally coupled to one another. So that is this kj is equal to k by n. That is the first thing that we do. And secondly, there is damping, but of course one can look at the over-damped system. What is the advantage that I get in going to the over-damped system? So that is the following, that here I have a second order differential equation, a differential equation that's second order in time. If I go to the over-damped limit, what is this over-damped limit? You assume this gamma to be so large that this inertial term can be neglected. The advantage that I get is that I go from this second order differential equation in time to a first order differential equation in time. Of course, you may say that why did you do? Well, we also looked at the second order, but you know, let's first look at the first order. Let's make life a bit simple, okay? But still you have the non-trivialities intact, namely there is a time delayed interaction, there is a disorder Pj, only that you reduced the order of the differential equation and you got rid of the underlying network structure. We will bring them in as we go along, but let's first look at this equation. There are n of them and these equations are all coupled. So the first thing that you do is you map it to a model which is very well known and popular in the nonlinear dynamics literature, that is this Kuramoto model. So what is this Kuramoto model? Let's just understand this, and it's actually a very simple model. So what you have is, you have n number of oscillators, limit cycle oscillators. What are limit cycle oscillators? You may recall a limit cycle oscillator is characterized by an isolated closed orbit in the phase space such that any initial condition that you start out from, any typical initial condition that you start out from, will eventually lead the dynamics to coincide with the limit cycle. Okay? So, so you have n coupled limit cycle oscillators. So theta j is the phase of the oscillator, that is, you have these closed orbits and each orbit is characterized by a particular frequency of oscillation. So this theta j is the phase of the jth limit cycle. Okay? And so d theta j dt equal to omega j, forget about the second term for the moment. The first term tells you that the rate of change of phase is equal to the angular frequency, which is the definition of the angular frequency, excepting that this angular frequency is different for different limit cycles. Remember, at the back of our mind, we have this picture that you have many generators and motors. Each one of them is rotating at a different frequency. Just as here, you have many limit cycles, each one is rotating at a different frequency, and so you have d theta j dt equal to omega j. But then there is interaction between the limit cycles, which is this mean field interaction, time delayed mean field interaction. The interaction between the jth and the kth unit is sine of the phase difference between the two, excepting that there is a time delay, tau. And you sum over all the nodes, okay? And you invoke mean field coupling, that everyone is interacting with everyone else equally well. And this omega j, as I said, it is like pj. You know, if you look at these two equations, they have the same mathematical form. If you look at these equations, these these two equations, they have the same mathematical form. Just as pj was a source of disorder, this like omega j, it is the frequency of the jth limit cycle. It is different for different limit cycles. So this omega j, it is a quench disorder frequency with a distribution. I mean, when you have a bunch of numbers, each one is different from the next one, then the best thing to do is to draw a histogram, and in the continuum limit, a histogram becomes a distribution. So there is a distribution with some mean omega naught. And in this picture, what I have done is that I have taken a certain number of oscillators. Each red dot denotes the phase of the oscillator at a particular instant, and I have drawn the phase. So phase being an angle between 0 and 2 pi will be denoted by a point on this circle. So this theta j, that is the phase of the jth oscillator with respect to some base level. Okay, so this is the equation of motion. You have many such limit cycle oscillators, each characterized by its phase. There is interaction between them. Each one has got a different frequency, and what we want to explore is the following: that given this setup, does this whole collection does this operate stably at a common frequency? That's the question that we are going to address, because this will address our first concern: is the power grid able to operate at a common frequency? And then we will explore its stability. Okay, so to characterize, you have this bunch of oscillators, each one is moving at a different frequency. Whether this whole collection is synchronized or not, that is, whether this whole collection is operating at a common frequency, you need to define a quantity that characterizes this collection at a macro level, right? And that is this order parameter r of t that I have defined here. It is just summation of e to the power I theta jt. Why do I do it this way? Because suppose if it so happens that these oscillators, if they are out of sync, that is, each one is rotating at its own frequency, there is no common frequency for the collection, then if I have a camera and I take a snapshot, then what I'm going to find is I'm going to find these phases to be kind of uniformly distributed on the circle. Okay? So if the points are uniformly distributed, then e to the power I theta j will be either +1 or -1 with equal probability, and then when I sum them up, I get 0. Okay, that's the unsynchronized state. While if it so happens that a good number, a macroscopic number of them are indeed in synchrony with one another, that is, the angles are changing such that there is a constant phase difference between them, constant meaning a phase difference that is not changing as a function of time. That is, you see that the points on the circle at a given instant are kind of clustered together. They are not uniformly spread. They are kind of clustered together. Then this e to the power I theta j will be +1 or -1 for a good number of them, and for the rest, let's say they are equally likely to be +1 or -1. Then this r is going to give you a non-zero value. So this, by looking at the modulus of this quantity, I am able to distinguish at the macro level whether the system is synchronized or whether it is unsynchronized. And since a picture is worth 1,000 words, so this is a video of what is going to happen, how the angles are changing as a function of time. This is when you have a synchronized system. You see that as a function of time, the thetas are changing. Of course, they will change, but then there is a constant phase difference between them, such that a big collection is rotating at a common frequency, while this is when the system is completely unsynchronized. As you can see, each point is going around at a different frequency. This is this like omega j. So the whole system is not synchronized, and the middle one is when you are at a transition point. I'll come to this transition later. So this is unsynchronized, the left one, the extreme right one is synchronized. And we would like to know, as a function of the different parameters in the system, when do I get a synchronized state, if at all I get a synchronized state, and what are the conditions to be satisfied. So the main queries that I would like to pose are, for a generic frequency distribution, that is, I don't tell you anything about the amount of disorder in the system. What is the source of disorder? This omega j. Each unit, each generator, rotor requires or consumes or generates a different amount of power. I don't tell you anything about the distribution. So for generic frequency distribution, what is the critical coupling at which the incoherent state loses its stability? That is, if I look at this equation, then one thing I notice at once, that suppose k is 0, there is no interaction, then of course you cannot have synchronization. So when k is 0, then you cannot have synchronization. When k is infinite, you would definitely have synchronization, because then everybody is interacting with everyone else with infinite strength. So therefore k 0, no synchronization, k infinite, definitely synchronized. So there must be a critical coupling at which the incoherent or the unsynchronized solution becomes synchronized. I want to know what is that critical coupling at which this happens, and the nature of bifurcation. Bifurcation, roughly put, is like phase transition. Of course, there are subtle differences. I'll come to them when I talk about. So here are the main results. So what am I doing here? So let's first understand this right-hand plot. What I have done is, so let's first understand the scenario. So I have this n-coupled differential equations, non-linear. I let the dynamics run for a very long time because I want to get to the stationary state, the long time state. Okay, I have prepared the system in some initial condition. I let the dynamics run for, let's say, some 10 days or something. In the stationary state, I want to know how does this system behave as a function of the parameters. In particular, I would like to know, is the system synchronized or is the system unsynchronized? Okay, so in the stationary state, I have plotted two scenarios which are possible that emerges out of our calculation. So this R mod, this is just telling you what is the amount of synchrony in the system, and the amount of synchrony can lie between 0 and 1. 1 means absolutely synchronized, everybody is happy with everyone else. 0 is everybody is unhappy with everyone else, and of course R can lie between 0 and 1. And what is this k? K is this coupling strength. K is telling you how much is the coupling interaction going on between the individual unit. And as I told you that k 0 means no coupling, then of course R will be 0, the system will be unsynchronized. And k very large, infinity, means everybody is very strongly coupled to everyone else, then R will be 1. And something has to happen in between. Now two scenarios may happen, is that as you jack up coupling k from 0 to a very large value, it may so happen that at a critical point, there is a jump. It reminds one of first order phase transition, that the system is unsynchronized, and suddenly there is a jump, the system becomes synchronized. Okay, and that's like a first order phase transition. Or the other possibility is, it is unsynchronized, and then gradually it gets to a synchronized state as a function of the coupling. So that is the red curve. That reminds one of the second order phase transition. Oops, sorry. Okay, so these are the two scenarios that you may envisage, that either there is a sharp transition, what we call a in the language of dynamical system theory, that's a subcritical bifurcation, or you may have a second order transition, supercritical bifurcation. Bifurcation just means that the stability changes. The system, one solution was stable in some parameter regime, it loses its stability, another solution pops up. So this change in stability properties is what is known as a bifurcation. Now what do I get out of my calculation? So this is what I have plotted here. So let me first tell you what the x-axis represents. X-axis represents tau. Tau is what? Tau is the amount of delay that is there in the system. Delay means what? How long does it take for a signal generated here to reach another node, distance, let's say 1 kilometer away. So that's tau. And what are these different lines they correspond to? Forget about this bimodal thing. For the moment, forget about this bimodal thing. Let's just concentrate on the first two lines. Okay, so this black line is Kc. What is Kc? Kc is this point, the point at which an unsynchronized solution becomes synchronized. Okay, the point at which an incoherent or unsynchronized solution loses its stability, it no longer remains stable, and a synchronized solution emerges. And what we see is that you see this oscillatory behavior, this black line. Just concentrate on this black line. So you see that as a function of the delay in the system, the point, the critical coupling at which the system becomes synchronized, that oscillates. It's kind of very strange when I look at it from, let's say, statistical physics perspective. It seems like, think of the, the magnetic phase diagram, that there is a critical temperature above which the system becomes paramagnet. So there is a time scale in the system, and it seems like in this system, the amount of delay, the time scale that is there in the system is playing a very crucial role in determining the value of the coupling. So this time scale is not something that can be scaled away. That, oh, there's a time scale, so I just renormalize time such that it goes away, and therefore you have a coupling which is independent of the time scale. That's not the case here. The amount of delay that is present in the system is going to tell you the precise value of coupling. Okay, that is still not so great an effect. But then what is the major consequence that is coming out? Now look at the red line. The red line is this one. That is also oscillating as a function of time. But occasionally it is going from zero, from negative to positive value. Negative to positive, and then again back to negative and positive and negative and positive and so on. So what is this quantity C3? This I will come to later, but basically this quantity is going to tell you whether you are going to see a first order transition or a second order transition. That is, whether you are going to see a subcritical bifurcation or a supercritical bifurcation. And what happens is that if you have a positive sign, then I'll come to it, but take me for granted at the moment that if you have a plus sign, then you have a first order transition. If you have a negative sign, you have a second order transition. So therefore, the first thing to note is that you have alternating first and second order transition as you change the amount of delay in the system. It's unlike what you typically come across in physics, that you have a time scale in the system, and the precise amount of time scale that you have, the precise value of time scale that you have in the system is going to tell you whether you have a first order transition or you have a second order transition. You have alternating first order, second order, first order, second order, something like that. Okay. So, so that's one main result. Maybe how am I doing with the time? Okay. So yeah. Okay. So that's one result. And secondly, this is for more mathematically oriented, like those of you who are more mathematically oriented. So this may appeal to you, that namely that for for like Hamiltonian systems, for what are known as integrable systems, you have this concept of Liouville-Arnold integrability. So basically what happens is that if a system is integrable, then in the phase space you are going to have a manifold such that your eventual long-time dynamics resides on this manifold. That is, here I have shown here a torus in this phase space such that a trajectory that starts out of this torus, out of this manifold, like eventually wraps around the torus and then remains confined to the torus, and that of course makes the system integrable, because you can discuss the dynamics in terms of what are known as action angle variables. So it leads to a huge simplification, because you have a large number of degrees of freedom, you have a very high dimensional phase space, but if the system is integrable, your eventual dynamics is confined to a low dimensional manifold. Okay, this is something which is known for integrable systems, and what we found is that based on our exact results, that for our system, which is not a Hamiltonian system, there is time delay interaction, there is dissipation and whatnot, and yet you find that in our case also you have a similar picture emerging, excepting that this manifold now resides in the function space, not in the phase space. Okay? Phase space is a space spanned by the degrees of freedom of the system. Function space is a space spanned by all different functions that you can think of in your mind that they describe the all different functions that describe the distribution function of the system. How many oscillators are there with this frequency and this amplitude, this phase, and so on. So this is the function space. Forget about the details, but this is the space of all possible distribution functions that you can think of. Let me just pause for a minute to explain to you why do you need a distribution function. You need a distribution function because you have very large number of units, they are all interacting. One way to deal with the system is to discuss its dynamics in terms of these coupled differential equations, but as a statistical physicist, the thing that you would like to do is to define a distribution function. How many oscillators are there? For example, let's say when we talk about COVID, how number of COVID patients in a country, instead of saying who is infected, you ask what is the total fraction that are affected at this level, what is the total fraction that are affected at that level, and so on. So this is this distribution function, and in the space of all possible distribution functions, there is a particular manifold which was first proposed by Ott and Antonsen, and what we could do with our method of analysis is to show that indeed such an ansatz can be rationalized, namely that there is a manifold which is attracting in this function space. Let me quickly tell you how did we go about doing it. That basically we invoked three different things. First of all, since you have many interacting units and you have indeed a large number of them, so you need to invoke kinetic theory that you must have read about. You need to know delay differential equations, because the differential equations are non-linear, that's okay, but they are also delayed. The interaction is delayed, and you need to do some non-linear analysis. So our method of analysis, let me just quickly tell you what is so this is the equation that you start out from, and then for large n you have a single oscillator distribution function. What is this guy doing? This guy is telling you how many oscillators are there with frequency omega and phase theta. Okay, because you have a big bunch of them. How many are there with frequency 5 Hertz and phase, let's say, 50 radians at time t? And of course, this is going to change because the thetas are dynamical variables. They change as a function of time. There is no noise in the dynamics, so the way it changes is by a kinetic equation, which is the equation of continuity. But it's a horribly complicated equation because of the time delayed interaction. Okay? So it's a nonlinear delay differential equation instead of the ordinary we all know about ordinary differential equation, partial differential equation, but delay differential equation is something that at least I was unaware of until I started working on this problem. And what did we do? Like, what are the main steps of analysis? You look at this equation, you want to know the stationary solution. You find out that the incoherent state, that is the state in which the thetas are unsynchronized, that is a stationary solution of this one. You do a linear stability analysis that will give you coupling. This is the critical coupling casing. That's up to that is quite straightforward. I think any nonlinear dynamics guy would do it, this linear stability analysis. But the main thing is to do the nonlinear analysis to find out the nature of bifurcation, and that's the nonlinear analysis that we do. This is the center manifold expansion, those of you who know about it. Details of analysis, maybe I skipped this part on the introduction of the delay differential equation. This itself is quite intricate because you need to define the dual space, the conjugate space, and of course the main thing is to define a scalar product. I mean, typically with normal differential equation, when there is no delay, it's quite straightforward, but for delay differential equation there is a good amount of work by Hall that we got, we could lay our hands on to define scalar product in this delayed in this context of delay differential equations. And well, details of analysis, I just quickly again go over. You have this differential equation. You find that the incoherent solution is a stationary solution. you look at perturbations, not necessarily small, because I am going to do nonlinear analysis. So this ft phi is the perturbation about the unsynchronized solution, and you find that the perturbation satisfies this equation where d is the part which is linear. So this is the part of the time evolution operator which is linear, but there is a nonlinear beast sitting here, this cal f ft, and we are going to do the nonlinear analysis. Of course, the linear analysis is quite straightforward. So what you find is that, of course, this has parallel in Landau damping in plasma physics. Those of you who come from that regime, what you find is that to find the critical coupling, you need to look at the eigenspectrum of the linear operator. You all must be familiar with. And what happens is that when k is smaller than the critical coupling, then your eigenvalues, they have a continuous spectrum occupying the imaginary axis. You don't have an eigenvalue with the real part. Okay? So therefore, the solution is neutrally stable. And of course, if the coupling is above a critical value Kc, then you see that a conjugate pair pops up, and that leads to the the incoherent solution becomes unstable, and then a synchronized solution takes over. That's the linear stability. The nonlinear stability, of course, requires the following thing. I don't know whether I'm able to, let me try. So you have this unstable subspace. So what is going to happen is that as you are changing the coupling, the linear solution is stable up to a point, and then the linear solution becomes unstable. So therefore, the solution leaves the unstable space. This is this unstable subspace, and then it hops on to this unstable manifold. Okay, this the linear space is a part of an nonlinear manifold, and the question is very close to the critical coupling. How do I define, how do I characterize the perturbation? Of course, what I do is that this line, the line at an angle that's going to describe the perturbation above, slightly above the critical coupling. So that will have components along the eigen basis. That's this AT P phi plus A star P star phi, plus there will be a nonlinear contribution, which is orthogonal to the linear subspace. And then one can write down an equation for this quantity A of t. What is A of t? A of t is the amplitude. That is going to tell me how does the instability grow as a function of time. So there's a long calculation that, of course, I don't have any time to tell you about. You can write down an equation of motion for A of t. It just tells you how does the instability grow as a function of time. And what you have is this sort of dynamics. A dot is lambda A by plus C3 A mod square A, which is, it has the same form as the pitchfork bifurcation in, the amplitude dynamics has the normal form of pitchfork bifurcation. And C3, you remember the C3 was what I was showing, that I told you to be determining the nature of phase bifurcation. This C3 has this very complicated form. The important thing to note is that I have disorder in the system. Okay, I'm not telling you the nature of disorder. It is this G omega. This could be a bimodal distribution, unimodal distribution, whatever. And yet, with our analysis, I am able to predict I'm able to write down an explicit expression for C3. Therefore, if you tell me the kind of disorder that's present in the system, I can at once tell you whether the system is going to show as a function of the delay a first order or a second order transition. And in fact, this is what I had shown here, that this is one picture that you may take back home, namely that the amount of delay is telling you whether you have a supercritical bifurcation or a subcritical bifurcation. So this time scale is going to play a very important role. What are the open issues? Of course, this is just the tip of the iceberg, because I made many assumptions. First of all, I said that every unit is coupled to everyone else with the same strength. That is, I did not take into account the nature, the underlying grid structure. That, of course, has to be taken into account. That's one. Secondly, I did a bit of cheating. I said that the time delay tau is just one number. But you think of a realistic situation, this tau is probably not probably, surely be a function of the separation between two units, because if in a grid structure, if I have two units which are very far away, it would take longer for the signal to traverse from one unit to another than the case in which the two units are very close together. So that's also a source of disorder that one has to take into account. Of course, we have done it also for higher order dynamics. I did this overdamped approximation to reduce the order, but this whole program can be carried out for higher order dynamics. So there are some questions like I talked about this manifold, and the question is, just as for integrable systems, you can write down the integrals of motion that characterize the manifold. Can one do such a thing for this Orton-Thomson manifold? And like as I told you, there is this network structure, and that can I take into account. So let me just summarize. We started out with spontaneous synchronization units, each one going his or her own way, and yet when you put them together, they all start to synchronize. They operate at a common frequency depending on certain conditions to be satisfied. Of course, it's not magic. You have to play with the parameters. But it turns out that this spontaneous synchronization, and especially power grids, it offers an emerging area in which you need to invoke a whole lot of results from kind of disparate fields, like let's say kinetic theory, theory of differential equations, and so on. So I'll just leave with this message that recent advances in bridging the scientific and engineering realizations of network synchrony, it seems to be quite an interesting thing to do if you want to keep the lights on and continue to optimize the brewing of coffee in the morning, which I understand is very important a task for all of us. So these are the references, and I'll just finish with a bit of commercialism. So we have recently written a book, not very recently, maybe 3-4 years ago, on statistical physics of synchronization, where we have summarized some of the results, while more results are underway. And I'll hopefully get another opportunity to talk to you about these new results that we hopefully will get in the times to come here again. Thank you very much for your attention.
Okay, so we have some time for questions.
Hello. Hi. I had a question that in which one of those graphs in which you were showing it was a first order transition as a function of k. Does that discontinuity becomes wider with system size?
Well, this is all done in the infinite system limit. Okay, if you take into account finite systems, you have to take into account finite size corrections. These are when you have a very large number in the thermodynamic limit, so to say. So therefore, you can characterize the collection by a distribution function. If you have a finite number of them, then you cannot characterize it by a distribution function, simply because the distribution function will not be well defined. It would have some spiky behavior. Okay. So this is in the infinite system limit. For finite system, of course, the whole thing has to be redone in a different manner.
So for infinite system, can I say that this values of order parameter you are getting between 0 and 1, is it continuous? Like if usually in first orders, there is a discontinuity, right?
Yeah, it is a discontinuous transition.
So 0 and then it becomes 1.
Close to 1. Okay, it depends on what value it gets to, depends on the details. Okay. But it's like there is a jump. It's not that 0 and then 0.01, 0.02, not like that. Okay. It's like okay. Of course, the exact value to which it gets, of course, depends on the details.
Hi, Jamik. Nice talk. Just wanted to tell you that because you mentioned that you want to eventually try putting a distribution of tau. Just wanted to tell you that in our work we used relaxation oscillators, not exactly Kuramoto, but the result should carry over. And like you, we wanted to simplify, not to actually put space, but still we wanted to have something of that. So we put distributions of tau. And then we realized that, you don't get such sensitive dependence on tau anymore. So in some sense, the distribution kills off all this critical dependence. I was wondering whether you have an insight on how that can
No,
arise?
we haven't. I mean, we are working on it, but at the moment I don't have something concrete to. But that's a very useful insight that you provided. I'll talk to you maybe
Sure.
and find out more details about it. Yeah.
Yeah, so you were discussing about this new manifold that you get
Huh.
of this function. So in the integrable system, of course, you have infinite conserved quantities, and that defines the manifold.
Yes,
so what is the analog of it in this kind of?
We don't know really, because this is something that I mentioned, no, in the conclusion slide, that can we construct this?
But even for Kuramoto model, you don't know.
No,
this.
we don't know. Can we construct such integrals for this manifold? We know that this manifold has been hypothesized by Otto and Antonsen, but then it was just an hypothesis, and what we could show that such a manifold exists in the sense, what does a manifold do? It tells you that if you start from this manifold, then your eventual dynamics remains confined to this manifold. Now, of course, the question is, I mean, there ought to be some integrals of motion, some constraints, like some conserved quantities, which are kind of confining the motion. So we don't know really what are they. And the main, probably, this is one of the reasons why we were unable to pinpoint them, is this factor of time delay. This time delay is kind of not allowing it to.
But the time delay is determining whether you have first order or second order
indeed.
transition.
Yes, indeed.
So that is very important.
Yes, indeed.
Okay. And another question I had was, you always talk about fixed point in this kind of equations. So is this time delay that is providing a fixed point, or how do you ensure that your nonlinear equation will always have a stable fixed point?
No, there's nothing that ensures, but what we have done is that we could write down the kinetic equation, the equation of continuity, and show that it has at least one fixed point, which is this incoherent solution. Of course, there could be other fixed points, and of course the synchronized solution is surely one fixed point, but that we were unable to pinpoint. What we did was, we showed that incoherent solution is one fixed point which is stable below Kc, and slightly above Kc it loses its stability, and then what we found is that it goes to a synchronized solution. Now, there could be many fixed points, like there could be many different types of synchronized solutions, stable fixed points that this equation may have. That is very difficult to at least analyze within this framework.
I was worried because if you go to some other fixed point, is there a way to come to this kind of stable fixed point? So what ensures that?
No, nothing. It may so happen that there could be many along the way, that what you are saying is that the incoherent solution becomes unstable, and then it gets to a stage which is not incoherent, but which is not synchronized either. I mean, it is synchronized marginally, let's say. There could be one, but what our simulations seem to suggest is that in these cases it gets directly to one, which has a good amount of synchrony.
Thanks again for the very nice talk.
Thank you.
Hi. So, sir, how crucial is this all-to-all connection for synchronization? I mean, can we not have 1-to-2 connection and then get synchronization?
1-to-2 connection meaning nearest neighbor connection.
1-to-2, yeah, nearest neighbor connection.
So what you can, at least for the case in which there is no delay in the system, there is a work like exact analysis by Strogatz that has shown that if you have only nearest neighbor interaction, then you cannot have synchronization in the system. For time delay, I would think that it would go through this sort of reasoning. But so what is going to happen is that you need to have some range of interaction, because what you want is you want a big number of them to synchronize. So just nearest neighbor will not do the job. But again, these things, unlike, let's say, in statistical physics, where you have, this model may remind one of XY, XY model and so on. The big problem is this time delay. So that kind of messes it up. Like XY interaction is instantaneous. And of course, that's a statistical system as opposed to this one, which is so you do not have kind of a Mermin-Wagner theorem and so on. So this kind of reasonings are not easy to construct, but at least for the no delay case, Strogatz has shown that you cannot have synchronization if you have just nearest neighbor interaction on a, let's say, 1D lattice.
Okay, thank you.
Hi, sir. So at the very start, you assumed weak interaction between the nodes. So at the very start, you assumed the weak interaction between the nodes, but you never used.
No, I used it. No,
Oh.
Weak interaction. So let me just tell you. The equation, this one. See, interaction between two nodes is weak. Indeed, how are K and J nodes connected to one another? What is the strength of coupling? It is K by N, right? K by N is the interaction strength between K and J, and N is very large. So therefore, the coupling between the two units is indeed very weak.
Okay.
Actually, if you don't have weak interaction, then this kind of model doesn't, you cannot even construct such models, because what you assume is that you have individual units which are described by limit cycle oscillators, and then the interaction is weak enough that you do not mess up the individual limit cycles. They continue to be limit cycle, excepting that there is slight shift in the frequency. If you have very strong interaction, then the individual dynamics gets messed up. Then you cannot construct such a phase model. Then, if you have strong interaction, then you better talk about one big oscillator rather than many, many oscillators. So you need this weak interaction.
One thing I wanted to ask was that, let us say you make all the Ks random, completely random, but you keep all-to-all coupling. Is there something interesting known about this limit?
Again, there is another source of disorder that you bring in, namely the coupling strength, right?
Yeah, but you keep all-to-all and you keep it completely random.
Yeah, but then, it would be like you put Kj here and you bring it in, right?
Yes.
Of course, this distribution has to be like, there will be like another parameter here, theta omega k comma t. That is, how many are there with coupling k, like amount k inside. That's what, and there is a distribution of this k. That's what you want, right?
No, I'm just saying that the strength of the coupling between J and K is completely random, that's all.
Yeah, completely random. And the meaning according to some distribution. There's an underlying distribution. Yes. So that, of course, brings in another source of disorder in the system. I do not know of any result. Excepting that sorry, just to interrupt you, excepting that what we know for sure is that if this Kj, that is the amount of coupling between K and J, if it is just nearest neighbor, then you do not have synchrony in the no delay case.
Yeah.
Okay, so you can put in some functional form, let's say, Kj decays as some function or something, we don't know. Of course, simulations are always possible, but this sort of analysis we haven't done.
Okay, the main reason for asking that is that there's some interest recently in quantum systems where you have like these all-to-all couplings, and then you look at the order n in the large n limit, you can get some exact solutions there.
I see.
So
okay.
Yeah,
so
the other thing was this: when you have this nearest neighbor stuff, but if you just introduce like these Griffiths effect or some very rare bonds which connect, then can you get synchrony again? Or?
Okay, so you have most of the nodes connected, but then there are a few long-range kind of couplings. Like again, this has also not been explored. Like as I said, that this kind of field is especially interesting when you bring in ideas from, like for example, I was completely new to this area when I started working on, and I had XY model in my mind. So therefore, of course, there are many directions to pursue within this framework, and there are no existing results that I am aware of.
Hi. So these results you have got for the strong damping case, you said. So what about like the weak damping?
Weak damping I mentioned. So then you have to really deal with the second order differential equation.
So any interesting dynamics would show up in that?
Roughly, I would say no, because basically, this is the result for the weak, finite damping case. Okay, there also you see that, of course, there, of course, one thing what happens is that, okay, one interesting, one technical thing that happens is that in equilibrium statistical mechanics, let's say within the Hamiltonian dynamics, the amount of inertia, the mass value, that doesn't play a role. Why? Because you have e to the power minus beta h, and h has got p square by twice m, so this m that you can absorb into p. So the amount of inertia that you have in the system doesn't affect the stationary state properties. Okay, what happens here is that because of this delay, the amount of inertia that you have in the system, that plays a role again in dictating whether you have a first order or a second order transition. This is the non-trivial part. Yet you have this kind of up down thing, subcritical, first order, second order, first order, second order. Whether you would get first order or whether you would get second order depends now on two factors. What is the amount of inertia present in the system, and what is the amount of delay present in the system.
I see. Okay, thank you.
So I will have like one last question and we'll just wrap it up. Shamik, this synchronized phase, right? How does it depend on the mean, like mean frequency?
Yes, indeed. This bunch is going around with the mean frequency of this distribution.
Oh, so the distribution, whatever the, like the frequency, it goes with.
Yes.
Okay, I see.
That there are many omega j's and there's a mean of the distribution. So when they are synchronized, a macroscopic number of them, there will be some outliers, of course they are not synchronized, but a macroscopic number of them in the thermodynamic limit will be going around with the mean of this distribution.
Irrespective of tau, like.
Irrespective of tau.
Yes. Okay. Thank you so much. Yes.
Thank you.
So since there are no more questions, okay, so let's thank Shamik again for this wonderful talk.
Thank you.
Okay, there is some tea and coffee outside, right? Huh? Hi.